we are going to be talking about how strong our network is. Okay, and what do we, well, let's look at the plan for this segment. Recall that in the last segment, we studied a randomized algorithm for matrix multiplication. And we introduced the probabilistic notion of correctness. What do we mean by an algorithm being correct with high probability? Okay. And in this current segment, we're going to look at the problem of how strong a network is. We're going to formalize it in the following way. We're going to define something called a min-cut in a graph. Informally speaking, it's the fewest number of edges that you need to remove in order to disconnect the graph. And that if that's very small, then the graph in some sense is not strong enough. And that's the intuition that leads to this formalism. And we present a very simple, elegant algorithm, a randomized algorithm to solve this problem. So let's look at the motivation. As I said, we're trying to figure out how strong a network is. So here are two examples of networks. The question is, which of these graphs or networks is robust? Okay. If you look at the one on the right, it is completely connected. So let's say we are play the devil's advocate. We want to disconnect this network. You would have to destroy a lot of edges before this network becomes disconnected. Even if you want to isolate one node, you will have to destroy all the incident edges, and that's a lot. On the contrary, if you look at this graph on the left, and if this is a network, you only have to delete that one link and you have disconnected this network. And so this makes this network very brittle. And so you want to find out how brittle or how easy to break your network is. And so we formalize it in the following way. We call this the min-cut problem. Okay. So we assume that our input is a graph with vertex set V and edge set E. This represents our network. So typically you can think of the vertices as being the computer nodes and the edges as being the ability for that two nodes can talk to each other. Okay? And so if you can create a cut in this network, that means there is a portion of the network that cannot talk to the rest of the network. Okay? And that's not a good situation. We want to avoid that. So a cut is a partition of the vertex set V into two sets S and the remaining V minus S. Okay? And the cut set corresponding to a particular cut is the set of edges with one end in S and the other end in V minus S. So all these edges that go across the cut are called the cut set. Okay. Our goal is to find the partition. We want to find the set S such that the corresponding cut set has the least cardinality. You want to find the smallest cut, and that's called the min cut. So we want to find the min cut. So the algorithm we're going to look at was invented by Karger, so we call it the Karger's min-cut algorithm. There is, we have to keep in mind that there is a flow-based algorithm that could do quite well as well, but it is still not very efficient. The most straightforward application of the flow-based algorithm would lead to something of the order of n to the 5. Okay? And we want to do better than that. Okay? So that's and moreover, the Karger's algorithm is very, very elegant and nice. So you'll see this. And the algorithm, here's the algorithm, right? It's very simple. You just repeat this process of contraction n minus 2 times, because each time you contract, you will be coalescing two vertices. So you can do that n minus 2 times before you're left with just two vertices. Okay, so repeat until the graph has only two vertices. Now, let's pick an edge uniformly at random from all the edges. A thing to note here is the graph, the way it will progress. You might end up having multiple edges going between vertices. So when you pick an edge, you should be careful not to pick two vertices and then consider the edge connecting them, because some edges could have a lot of some vertices, some pairs of vertices could have a lot of edges going between them, and others maybe much fewer. So you really have to be careful to pick the edge uniformly at random over the set of all edges. Okay, so if there's two vertices between which there's a lot of edges, and another so for example here, let's say this one has lots of edges going between them, and there's another pair of vertices and you only have one edge going between them. The probability this one edge is chosen should be exactly equal to the probability that this other edge over here is chosen. Okay, so pick such an edge uniformly at random, and then you look at the two vertices that it's connecting. So let's say this is U and this is V. Now, knowing that this edge is connecting U and V, we have to contract or coalesce U and V into a single vertex. So you have to contract that edge. Okay, and when you do that, so for example, now if you contract U and V, then let's add a couple of more edges to illustrate the point. Let's say this is our graph. When you contract U and V, you have to put U and V together as one vertex. So this is the coalesced vertex UV. Okay, and let's just call these X and Y. Okay, so all these edges that go between U and V will form self loops when you contract them. So they are all removed. So you remove all the self loops, just don't consider them. Okay, but you need to be careful about the other edges though. So let's put down X and Y, and you have let's look at the there is one edge going between U and X. Now there's no U, there's only a UVs, but that edge still has to be put in over here. And between V and X there is an edge, so that has to be a separate edge. Between V and Y there is an edge, and between X and Y there previously was an edge. So this is the new graph that we get. Okay, so this is the algorithm. You just keep contracting. You pick an edge uniformly at random, you contract it and create a new graph, and this new graph will have one fewer vertex. But keep in mind, some of the vertices are going to become these sort of compound vertices that contain multiple original vertices in them. Okay, so we do this until we're left with just two vertices. Okay, and when we're left with two vertices, what will the picture look like? Well, it's going to look something like this. There's going to be two sort of giant vertices that include a lot of coalesced original vertices, and then there's going to be edges across them. Okay, and all the vertices in one of these the original vertices in one of these these sort of coalesced vertices, you call them S. So all the original vertices in the other coalesced vertex is going to be V minus S. At least this is going to be our candidate S and V minus S, and our hope is that this edge set will be the min cut. Okay, and this of course is not guaranteed, but we hope to be able to show that with some reasonable probability, indeed that will be the min cut. Okay, so let's look at the execution of this algorithm in this example. So here you have a sequence of graphs. Okay, this is the original graph. Okay, this is the original graph, and we have chosen to contract this vertex, so this edge. Okay, and because of that contraction, it's the two vertices have become one vertex. Okay, and now there are 1, 2, 3, 4, 5, 6 edges going away from these pair of vertices. So those 6 edges must find their way. Oh, actually, there's a 7th one over here. So those 7 edges must be here, and you notice that's the case. There are these 7 edges that are incident on this new coalesced vertex. Okay, all this there must have been one self loop that was created that was removed. Okay, and now you pick one more edge to contract. This is the edge that is chosen for contraction, and after contraction you get this coalesced vertex, and you continue on. Okay, so now you have chosen to contract this edge, and you get this vertex as the coalesced vertex. Now notice that you are trying to contract this edge, and you get this coalesced vertex, and you continue on. Okay, so you've chosen to contract this edge, you get this coalesced vertex, and you continue proceeding this way. You're left with 2 final coalesced vertices, and you're left with these 3 edges. And incidentally, these are all this coalesced vertex and this coalesced vertex respectively contain all these vertices and all these vertices respectively. And if you think about it, the min cut indeed was this these 3 edges that separated the top from the top 5 vertices from the bottom 5 vertices. And so this shows an example of a good run of this algorithm, because it has actually led to us finding the min cut. Okay, but of course that is not at all guaranteed. It's a probabilistic thing, and you need to be able to show that this happens with some reasonable probability. So let's try to analyze that. Okay, so what is it that we are going to prove? Let S be the set of original vertices that led to one of the final 2 vertices. So remember, the algorithm ends with 2 final vertices, and let S be the set of original vertices that led to one of the final 2 vertices. Okay. Now with probability at least 1 over n choose 2, so that's 1 over some polynomial in n. S and V minus S induce the smallest cut. So the cut set produced in this way is going to be the min cut with probability at least 1 over n choose 2. Okay, so this is what we need to show. Okay, so, I noticed that this probability is fairly small. It's just 1 over some polynomial in n, but bear with me. We'll figure out how to deal with that. Okay, so how do we prove this lemma? Okay. Actually, we don't care about all possible min cuts. You know, a graph can have lots of min cuts, and good exercise for you to would be to come up with graphs that have lots and lots and lots of min cuts. Okay, so now let's pick one min cut. Okay, let C star be a cut set, a min cut of minimum cardinality. Okay, so instead of proving something strong like the probability of finding any min cut is blah, we're just going to limit show that even finding this one particular min cut, finding the probability of finding this one particular min cut is at least 1 over n choose 2. Okay, and this is actually good enough if you think about it. Okay, so we're going to limit ourselves to this proving this. Okay, so let's try to figure out how to do that. Okay, think about how this event may fail to happen. What could go wrong? Okay, as long as the edges that you keep picking are avoiding the min cut, this particular C star. Let's say that there's a graph. It looks something like this, and this is the min cut. This is the C star that we're talking about. As long as the contractions happen over in other edges that are not part of the min cut, we're going to be fine. The min cut is going to survive till the end. Okay? The moment we pick a min cut edge, we have lost it. Okay? So that's the intuition that we want to formalize. Okay? So towards that, let E1, E2, and so on up to En minus 2 be the sequence of edges contracted by the algorithm. Okay? Now, as I said, if one of these E1 through En minus 2 is a member of this min cut, that's bad. Okay, so the other way of saying is that the algorithm succeeds is if none of them are in C star. Okay, so this probability that we care about, probability that the cut produced by the algorithm is in C star, is equal to the probability that the last edge that we contracted was not in C star. The last but one at the edge that we contracted was not in C star, and so on up to the first edge that was contracted. Okay, so I've just gone in the reverse order for a reason. Okay. So now this is the probability of the intersection of several events. So all of these things will have to happen in order for the algorithm to succeed. Okay, so a lot of stars have to line up. So let's, but we, let's see. But the one thing we need to be careful about is these are not independent events. There could be dependencies. So we should be a little bit careful. We cannot just multiply their individual probabilities. But given this situation, we can write this intersection of all these probabilities in the following manner. You isolate the probability, the conditional probability of just the very first event listed over here, conditioned on all these other things happening. Okay. But if you were to do that, then you also will have to multiply it by the probability of whatever condition you imposed. Okay, so that same thing is written over here. But now the same structure holds over here. So here, if you notice, it's just the probability of the intersection of several events, except En minus 2 not in C star has been removed, but the rest of them are all intersections of events. Okay, which means we can repeat the same procedure. You isolate En minus 3 does not belong to C star, conditioned on the rest of them. But then if you were to do that, you would have to then multiply it by the probability of this condition, which means then you can isolate En minus 4 conditioned on the remaining intersections, and so on. So when you work that out, you're going to get this sequence of conditional probabilities. And the last one, of course, is you're going to end with probability of E1 not in C star, after which you cannot apply this any further. Okay. So this boils down to computing one such conditional probability, because really the probability that we want is the product of a sequence of such conditional probabilities. Okay, so by now you may be wondering, what is the intuition? Okay, so let's actually look at a picture that gives us the intuition of exactly what happens. Okay, let's think of the execution of this algorithm, okay, at the very beginning, you are in some state, you have still not picked any edge. So then you pick an edge. Okay, that edge could be a member of the min cut C star or not. If it is a member of the cut C star, basically what that means, the very first edge that you picked, if that belongs to C star, okay, that's very bad. Your this execution will not succeed. Okay, otherwise, something good happens. E1 is not in C star. Okay, good, great. So then the execution has survived the first iteration. Okay, but then again, the second edge that was chosen, E2, if it belonged to C star, again we're out of luck. So the execution has veered off into a bad situation. Otherwise, it's good. Okay, and this continues on. Okay, so at any point in time, let's look at what is the what happens. Well, if you have managed to reach this point, okay, that's basically saying, let's say that there was a sequence of executions. This is the ith iteration. How can you say that the ith iteration will succeed or fail? Well, first of all, you should have reached the ith iteration. Okay, what does it mean to have reached the ith iteration? All of these were good. Okay, all of these had to have been good. Only then you would have even reached here, and that's exactly what is captured by this condition. All of the previous edges, EI minus 1, EI minus 2, and so on up to E1, all of those edges must have missed the min cut. Only then you would have even come to this point, and then conditioning, having come to this point, now you can ask what is the probability that you would either go down this bad path, or you would continue. You would continue to be in the good path. Okay, and that's exactly the intuition here. Okay, so now that we can come back to the formalism here, let's look at this. Let's look at each of these conditional probabilities, right? So in particular, so we are going to focus on this this one conditional probability, right? So let's get the right expression for that particular probability. Let's denote the size of the min cut as k. Now, if you think about it, as the as the edge contractions take place, the degree of the graph that we obtained is never going to be less than k. Why is that? Well, if you look at any cut in the graph as the algorithm progresses, let's say in the ith iteration, okay, any cut in the graph actually corresponds to an original cut in the original graph. So if the number of edges going across the cut that you chose in the ith iteration is less than k, it's also going to be less than k in the original graph. So k is going to be a lower bound on the min cut as the algorithm progresses. So all the graphs that we encounter till the very end is going to have a min cut of size at least k, which means the degree will also have to be at least k. Because if the degree is smaller, then you can create a cut. You can the low degree vertex can become one side of the cut, and all the other vertices can become other side of the cut. So clearly that's the minimum degree of the graph G that we have is at least k. Okay. And as I mentioned, this is going to be the case throughout the execution, right? So any look at any coalesced vertex. So this has a lot of the original nodes, and if you look at all the edges going out of that node, it it cannot become less than k. Okay. So just before the ith contraction, okay, how many vertices are there? Well, I minus 1 contractions have taken place. So you're left with n minus I, you'll be left with n minus I minus 1 vertices, which is n minus I plus 1. Okay. And each one of them has degree at least k, right? So if you count the how do you count the number of edges? Well, actually, let's count the total degree. There are n minus I plus 1 vertices, each of degree at least k. Okay? But if you count the total degree, that double counts the number of edges. So if you divide by 2, you will get a lower bound on the number of edges. Okay? So now let's go back to this probability. Remember, this probability term is what we want to compute. Okay. We know that the total number of we know that the number of edges is at least this quantity. Okay, and we've reached the ith execution without destroying the min cut C star. Okay, how do we ensure? So, what is the probability that the ith edge that is chosen also avoids the min cut? Okay. Well, that's going to be at least the probability that the ith edge is part of the min cut. So this is the probability of a good event. Okay, this is the good event, that the ith edge did not belong to the min cut. That's going to be 1 minus the probability of the bad event, which is that the ith edge is a member of the min cut C star. Okay. So this is going to be the probability that the ith edge is a member of the min cut. That's what we need to put here. So how do we get this expression here? Well, there are k edges in the min cut. Okay. If you choose one of them, which you will do with probability k over the set of the size of the total number of edges. Okay. If you so this is going to be the probability with which you're going to choose one of these min cut edges. So this is going to be the probability of the bad event. Okay. So if you do 1 minus the probability of the bad event, you will get the probability of the good event, right? And keep in mind that this is just the lower bound on the size of the on the number of edges. So when you replace the total number of edges by a lower bound, okay, this whole quantity can become a little bit larger. The probability of the bad event could become large, potentially a little bit larger. So 1 minus of this, therefore, it could only be a little bit smaller, and as a result, you will have this inequality here. It's greater than or equal to this whole thing on the right hand side. Okay. So now, if you work that out, it's going to come out as n minus I minus 1 divided by n minus I plus 1. Okay. This is the expression we get for this one probability term. So now going back to this original probability that the cut produced by the algorithm is C star. Remember, we wrote that as the product of multiple conditional probabilities, and for each one we have n minus I minus 1 divided by n minus I plus 1. So if we plug that in, we get this telescopic product. And nice thing is there's going to be a lot of cancellations. This n minus 2 will cancel out with this one. There'll be an n minus 3 cancelling out with the next n minus 3 over here, and so on. So here, if you see, the 3 will cancel out over here, 4 will cancel out over here, and so on. So what you'll be left with is these two terms in the denominator and this 2 here in the numerator, which is exactly what we want. So with that, we have proven the lemma. Okay. So now we need to figure out a way to boost the probability of success. Remember, now we only have a probability of success that is something like 2 over n into n minus 1. And that's pretty low. Okay. So let's figure out let's see what happens when we repeat this some number of times. So let's, in particular, we're going to repeat it this many times. Okay. And let's see what happens. What is the probability that all of these repetitions, this c times n choose 2 times log n number of repetitions, what's the probability that all of them will fail? Well, the probability that one of them will fail is at most 1 minus 1 over n choose 2. Okay, the probability that all of them will fail, and these are all independent repetitions, is just the product of this this many times. So you can just raise it to the power c n choose 2 times log n. Okay, and we have this inequality. 1 minus x is at most e to the minus x. This is a commonly used inequality. So this 1 minus this quantity can be written as e to the minus 1 over n choose 2. Okay. But then you also have this in the exponent. So the new e to the, you get overall, you get e to the minus this exponent. Okay. The nice thing is there's this n choose 2 over here and n choose 2 over here. They cancel out. And you can take the c as log n the whole raised to the power c. So you finally, this works out to 1 over n to the power c. Okay. So the nice thing is now what we have shown is that the probability that all of these repetitions will fail is at most 1 over some arbitrarily large polynomial in n. Okay. So this leads us to the algorithm that will succeed with high probability. You keep repeating the algorithm, this contraction algorithm that we have discussed. You repeat that this many times, c times n choose 2 times log n times. And each time you repeat, you see what is the min cut that you get. If it is better than all the min cuts that you've seen before, update it. Okay. So at the end, you would have the best min cut that you've seen in all these many repetitions. And that min cut is going, that candidate min cut actually will actually be the true min cut with probability at least 1 minus 1 over n to the c. Okay, and that's exactly what we mean by with high probability. Okay, so that's good. So we've got the algorithm working correctly. What we need to do is make sure that we have not designed a very bad algorithm in terms of running time. But keep in mind that this is a Monte Carlo algorithm. We are not guaranteed to have found the min cut. We're guaranteed that the min cut that we produce is going to the cut that we claim as the min cut is indeed going to be the min cut with high probability, but not guaranteed. Okay. And this Kargar's algorithm, this contraction algorithm, can be carefully designed to run in O of n squared time. So the overall running time, because remember we have to also repeat this another n choose 2 times log n number of times. So the overall running time is going to be O of n to the 4 log n. And that's going to be better than the flow-based algorithm. Okay. So let's conclude this segment. We've studied the problem of finding a min cut in a graph. We discussed an elegant randomized algorithm invented by David Kargar, and show that if you repeat it appropriately, it's going to be correct with high probability, which is faster than the usual deterministic algorithm that we think about in this context. Okay. In the next segment, we're going to study Bayes' law, and we'll see it via an example where we need to understand something about the world around us. We will repeat some experiments, and as we run these experiments, we'll get a better and better understanding of the world around us. And that's what we mean by I mean by this, this prompt for the next segment: how to understand the world around us. Play with it, run some experiments, figure out, update your understanding of the world. Okay. So with that, we end this segment.